Now we're continuing with the relationship between electricity and magnetism, and we're going into a new thing. It's called induction. It's going in sort of the other direction. So instead of talking about the magnetic field that's produced by moving charges, we're going to talk about what it takes for a magnetic field to produce an electric current. And that's called induction. And the first concept that we're going to talk about with induction is first, I haven't given you any background on why this will be useful, but we're going to introduce the idea of magnetic flux. So you can think of this as kind of like a mathematical preliminary thing, just understanding what this is. Magnetic flux. And we're going to use capital Greek letter phi to represent the magnetic flux. And so if you have a closed loop of wire, this wire needs to be a conductor so that electric current can go through it. And say that this has an area A, then first define a line that's perpendicular to this loop. Okay, so in the one that I've drawn, which is in the plane of the page, the perpendicular line would be out of the page and into the page. Okay, that's a perpendicular line to that surface. And now we'll define an angle theta. So this theta is the angle between the magnetic field vectors. And we're always going to assume that there's a constant magnetic field vector inside this loop, that this loop is surrounded by. That obviously doesn't have to be the case always, but these are the calculations we're going to do. And so there's going to be a constant angle between this magnetic field vector B and that perpendicular line that we defined. Okay. Then the magnetic flux is defined as the magnitude of the magnetic field vector times the area times the cosine of this angle theta. And the SI units of this magnetic flux are Tesla meter squared. You can just see that from the definition. You have the Tesla from the B, the meter squared from the area. So that's where that comes from. So what does it mean having this angle in here? If the magnetic field vector is perpendicular to the loop, then that means that it's parallel to that line that we defined that's perpendicular to the loop. And then in that case, the magnetic flux is just going to be the magnitude of the magnetic field times the area. And at the other extreme, if the magnetic field vector is in the same plane of the loop, then the magnetic flux, no matter what the magnetic field vector is, no matter what the area is, this will be zero. Because that angle theta that we defined will be 90 degrees, and the cosine of 90 degrees is zero. Let's see a couple of calculations. Hold on a second. Okay, so the first example, let's say that we have a circular loop of wire And this circular loop of wire exists in a constant magnetic field that's pointing into the page. And this loop of wire has a radius of 0.10 meters, and the magnitude of this magnetic field everywhere is 0.20 Tesla. And we want to know the following things. First, what's the magnetic flux? Second, what's the magnetic flux if instead of being positioned like the drawing here, we rotate those magnetic field vectors 20 degrees, so everything is at an angle of 20 degrees. So we're going to rotate that magnetic field vector 20 degrees. And then third, if instead of rotating the magnetic field vector 20 degrees, the magnetic field vector goes back to being straight into the page, what's the magnetic flux if we, instead of rotating that magnetic field vector, rotate the loop 20 degrees? Okay, so for part A, the magnetic flux is equal to the area, so that's pi times the radius squared, times the magnitude of the magnetic field vector. And if you multiply that all out, you get a magnetic flux of 0.00628 Tesla meter squared. And now we'll think about rotating those magnetic field vectors. So now the magnetic field vectors make an angle of 20 degrees with that perpendicular line. And so this magnetic flux is going to be this same stuff we just calculated in part A, but then we're going to multiply it by the cosine of 20 degrees. So I'll just do this as 0.00628 times the cosine of 20 degrees. And that comes out to be 0.0059 Tesla meter squared. Okay, so as you change that angle, as that magnetic field vector moves away from being perpendicular to the loop, that cosine makes that value get smaller. Okay. In this case, we can see these two values for part A and part B are pretty close to the same because the cosine of 20 degrees is pretty close to 1. It's 0.940. So that's why we get an answer that's pretty close to A, but it's not quite as big as A. And as this angle gets closer to 0 degrees, you get closer to 0.00628. As it gets closer to 90 degrees, you get closer to 0 for the magnetic flux. And now what would be the magnetic flux if instead of changing the angle of the magnetic field vector, we had the magnetic field vector going straight into the page, but the loop changed? Well, that's going to have the same effect as rotating the magnetic field vector, because what it does is it changes the angle of that line that's perpendicular to the loop. So if this loop was rotated 20 degrees, that perpendicular line would be rotated 20 degrees, and we would still get the same result. We'd have 0.0000628 times the cosine of 20 degrees again, and that's equal to the same thing we got before. Okay, let's see another example. So this time, let's say that our loop of wire is a rectangle, and it has a height of 0.10 meters and a width of 5 centimeters, 0.05 meters. And the magnetic field vectors are going this way. And the magnitude of these magnetic field vectors is 0.5 Tesla. Okay. And what we want to calculate is first the magnetic flux as it's drawn. And then second, we want to calculate the magnetic flux if we rotated this loop 30 degrees. Okay, well, for the first one, now the magnetic field vectors are going straight to the right. A line that's perpendicular to this loop is going straight out of the page. So the magnetic field vectors are 90 degrees perpendicular from that perpendicular line, the line that's perpendicular to the loop. And so what we have is the magnetic flux is equal to the area, I'm not going to calculate that yet, you'll see why, times the strength of the magnetic field, which is 0.5 Tesla, times the cosine of 90 degrees. The cosine of 90 degrees is 0, so this just comes out to be 0. Okay, but what if now we rotate this loop a little bit from the way it's drawn? So we're going to rotate the loop 30 degrees. What that means is if it starts out at the perpendicular line to this loop is 90 degrees from the magnetic field vector, and we rotate it 30, now it's going to be 60 degrees from the magnetic field vector. So we have a magnetic flux that's equal to the area, so that is 0.1 times 0.05, and then multiplied by the strength of the magnetic field vector, that's 0.5. And this time, the angle we're taking the cosine of is 60 degrees. And so we get a magnetic flux of 0.00125 Tesla meter squared. And now we can talk about induction. So induction, as I said, is when a magnetic field produces an electric current. And the mechanism for this is that a changing magnetic flux produces a current. So it's not just the magnetic flux that matters, it's how the magnetic flux is changing. So a changing magnetic flux produces, or I guess what you say really is induces, that's what, induction means, that this is induced, a current in the loop. And the equation for calculating the amount of current is Faraday's law of induction. And we're going to use Faraday's law of induction to give us the magnitude of the current. And after this, I'll talk about how to determine the direction of the current. So this is the magnitude of the induced current. And Faraday's law of induction says the EMF, so what's produced by this changing magnetic flux is an EMF, a voltage, a potential difference. And this EMF is equal to negative N, I'll give you the definitions of these things, times the derivative of the magnetic flux with respect to time. Okay, so first of all, this negative sign is referring to a direction. You always see this in the equation, but since we're just using this for the magnitude, we're going to always just forget about that, okay? So you'll always see that when you see Faraday's law of induction, you're always going to see that negative, but remember that that does not concern us. And then N is the number of coils, or the number of loops in this conductive wire. Remember, we saw that before also in calculating the magnetic field that's produced by a current around a set of loops. So this is the number of loops. And so you can see you get a bigger EMF the more loops you have. And you can think of there being sort of 4 ways that this can happen. So in order to produce this EMF, there has to be a change over time in the magnetic flux. So you can think of there being kind of 4 ways to induce this EMF, or let's just say the current. That's what we're trying to get to eventually, is the current. The first way is the magnitude of the magnetic field can change. The second way is the magnitude can stay the same, but the direction can change. So I'll write this as a vector this time since we're talking about direction. The third way is the area of the loop can change over time. You'll do at least one problem where the area of the electric wire changes because you sort of squish this circular shape squish the walls of this circle together, and it goes from a big area to a small area. And then the last way, the fourth way, is the orientation of the loop can change. And of course, you can have any combination of these. You could have any one of these, any 2 of these, any 3 of these, all of them, and together they determine that derivative of the magnetic flux with respect to time. Okay, so let's see how this works. Remember, so far we're just calculating the magnitude of this induced EMF, and then we'll use that to calculate the induced current. So for the first example, let's say we have a magnetic field with a magnitude of 0.005 T. Okay, so that means as time increases, the strength of the magnetic field is increasing, and our loop of wire is a circular shape with a radius of 0.2 meters. And this magnetic field everywhere is directed out of the page. And it's constant. We need that in order to do these calculations. Okay. So it's always pointing out of the page, but it's pointing out of the page with a magnitude that's equal to this function of time. And let's say that the resistance in the loop is 0.1 ohms. And we want to calculate the magnitude of the induced current. Okay, so ideally we would like to know the magnitude and the direction of the current. Is it going around this loop clockwise or counterclockwise? We can't do the direction yet, although that's the next thing we'll talk about. Okay, the first thing we have to do is figure out the derivative of the magnetic flux with respect to time. Well, we know that the definition of the magnetic flux is the area times the magnitude of the magnetic field times the cosine of the angle between that perpendicular line and the magnetic field vectors. In this case, we have an area of, so just using pi r squared for the area, this is 0.1257. I'll leave it there. And now we're multiplying it by the strength of the magnetic field. Now notice that what I'm calculating, since the strength of the magnetic field is a function of time, in this case we're going to get the magnetic flux as a function of time. So we have this times 0.005 T. And so we get 0.000628 T. That's the magnetic flux as a function of time. Most of the time when we calculate the time derivative of the magnetic flux, we're going to use a difference equation where we just have the change in the flux divided by the change in time. But in this case, we can actually calculate that derivative exactly. So the derivative of the magnetic flux with respect to time is the derivative of this. And so we just get 0.000628 using the polynomial rule for derivatives. And now we can plug that into Faraday's law of induction. So the induced EMF is equal to negative, there's only one loop, and so it's just negative 0.000628. Remember that negative, it always shows up when you see this equation, but it's no use to us. And EMF is, if you're in SI units, that's in volts. So there we have our EMF. And now you can use, since this wire has a resistance to it, you can use Ohm's law to calculate the induced current. And so the current is equal to the voltage divided by the resistance. So that's 0.000628 divided by the resistance in the loop. And we get a current of 0.00628 amps. Okay, before we go on to figuring out the direction, let's do one more example where we use the approach that I think you use in all the homework problems, where instead of calculating a derivative, you do a difference equation. So as another example, let's say that we have a magnetic field that's going into the page everywhere. And we're going to start out with a loop like this. And this has a radius of 15 centimeters, 0.15 meters. And the strength of the magnetic field everywhere is 1 Tesla. And this time what's going to happen is this is going to go from its circular shape, and then it's going to be squished flat. So we're going to go from the area of the circle to, we're going to assume that it's at 0 area, and this all happens over 1/100th of a second. And we're going to calculate the magnitude of that EMF. Okay, so this time we don't have a way to calculate the magnetic flux as a function of time. We can just calculate it at 2 different instants. So at the first instant, I'm going to call our magnetic flux phi1. And that is equal to, if you calculate the area of this circle, pi r squared, you get 0.071 meters squared, times the magnetic field magnitude with 1 Tesla, so times 1. In this example, just like the last one, those vectors are perpendicular to this loop, and so the cosine that you're using is the cosine of 0, which just comes out to be 1. And so we get at the first instant, before this is squished, you get a magnetic flux of 0.071 Tesla meters squared. And then at the second instant, 0.01 seconds later, the area is 0, so the magnetic flux is 0. And so now we can approximate the derivative with respect to time for the magnetic flux. It's going to be the later magnetic flux minus the earlier. Divided by the elapsed time. And we get a value of, well, this is really 0.0707, so this comes out to be 7.07, and this is Tesla meters squared over seconds. Well, it comes out to be negative, but notice that, we don't care about these signs, and so, again, I'm going to just forget about that. Since there's only one loop here, now the induced EMF is equal to, now I'm using Faraday's law of induction. We have the negative d phi dt, so that's negative 7.07 volts. Again, we don't care about this. And so you have a voltage of 7.07. And if we knew the resistance of this loop, we could figure out the current that's being induced around this loop. So now we can talk about how we figure out the direction of that current that's induced around the loop. So now that we have a way to calculate the magnitude, we can think about the direction of the induced current. And the rule for calculating this direction is called Lenz's law. And you can word this a few different ways. This is the best I can come up with. The induced current in the loop produces a magnetic field. We know that from, I guess, the last lecture. If you have a current in a loop, you get a constant magnetic field acting perpendicular to the current. And the direction of that magnetic field opposes the change in flux that caused it. So you always have an original magnetic field, and then you have an induced magnetic field. And the sum of those two fields always has a smaller change in flux than just that original magnetic field did by itself. Okay, the new one that's induced sort of softens the effect of this change of magnetic flux. Okay, so let me show you how to think about this. So let's say that we start out with a circular loop and a constant magnetic field that's pointing out of the page. And this loop has a radius of 0.05 meters. And the magnetic field has a strength of 0.3 Tesla. And then what we're going to do is rotate this loop on its axis. So you can see this is sort of a rotated loop, and we're going to think of it being rotated this way. Okay, so this is the side that's out. This is the side that's out closest to us. And then this side is farther away. Okay, as it rotates. And so you can see that what we're going to get is we're going to get a reduction in magnetic flux as time goes by. And we'll say that this angle, we rotate an angle of 30 degrees in 1 millisecond. So this thing is spinning around really fast, and we're going to do this calculation using 30 degrees. And so if we know that the resistance in this wire is 0.1 ohms, what's the induced current in the wire? With the direction. So we're going to use Faraday's law to calculate the magnitude of the current. And we're going to use Lenz's law to figure out the direction. Okay, well, we're going to do this as a difference equation. So first I'm going to do Faraday's law. So at the first instant, when the magnetic field is perpendicular to this loop, this phi1 is equal to the area of that loop, which I calculated 0.007854 times the magnetic field strength, which is 0.3. At that first instant, the magnetic field vector is parallel to the perpendicular line. And so this is cosine of 0, which I can just leave out because it's 1. And so this comes out to be 0.002356 Tesla meters squared. And then at the second instant, the only thing that's changed is the angle between the perpendicular line and the magnetic field vector. So I'll write this as our original value now times a cosine of 30 degrees. And this comes out to be 0.002041 Tesla meters squared. So now to approximate that derivative with respect to time, the derivative of the magnetic flux with respect to time is the later flux minus the earlier flux divided by the elapsed time. And so we get a value of negative 0.316, and this is Tesla meters squared over seconds. Well, in order just to use Faraday's law, we don't care about this negative. But to use Lenz's law, this is going to be important now because we know now that the magnetic flux is decreasing. And so when we get to Lenz's law to determine the direction of the induced current, we're going to know that the induced magnetic field is in whatever direction is required to increase the magnetic, the change in magnetic flux, to increase the magnetic flux, okay? Because it always fights that change. Okay, so first we'll use Faraday's law. Computer issue, just a second. So Faraday's law says, don't worry about any of the signs. The induced EMF is equal to negative of negative 0.316. We just never care about these. And so you get an EMF of 0.316 volts. And now what we want really is the induced current magnitude. This is the voltage, the EMF. And so we can use Ohm's law, and that says that the induced current is equal to 0.316 divided by the resistance. And so we get a current of 3.16 amps, big current. That's the induced current. But now for the direction. And this is the one that is going to take probably a little more practice. So what we know is that, notice that this magnetic flux is decreasing. We saw that when we calculated that derivative. So we want our induced magnetic field to increase the magnetic flux. That means it has to be in the same direction as the original magnetic field. So since this magnetic flux was decreasing, the induced magnetic field causes an increase in magnetic flux. And what direction would it have to be to increase the magnetic flux? It would have to be in the same direction as the original magnetic field. Okay, so now if this is our loop, our induced magnetic field is coming out of the page. We figured that because it's the same direction as the original magnetic field. And now the right-hand rule says for a current to produce a magnetic field coming out of the page, it has to be going this way. So now we know that the induced current has a magnitude of 3.16 amps, and it's going counterclockwise around this loop.